Okay, so we finished the last part talking about how variable stars could be used to try to figure out distances, the tremendous distances that we have to figure out within and outside of our galaxy. We talked about Cepheid variable stars, which seem to vary very slowly if they were intrinsically bright, and seem to vary very rapidly if they were intrinsically dimmer. And still, even a dim Cepheid is a pretty darn bright star. Once Henrietta Leavitt found this period luminosity relationship, basically the brighter the Cepheid variable, the longer it took to vary, we could actually, once that was calibrated, we can actually say, okay, here's a Cepheid variable that takes 30 days to vary. That means that it must be 10,000 times as bright as our sun, because it's pretty close to this area here on the chart. And so I know that that star is 10,000 solar luminosities. And if I compare that with how bright the star actually is, I can figure out how far away that star is, and I can figure out how far away either that star cluster or galaxy that star is located in is from me. And that's very important because just about a century ago, a little more than a century ago, astronomers thought that we were at the approximate center of the Milky Way, a disk of stars that form the Milky Way. We see in the night sky that the Milky Way is a band of light, so it's pretty obvious that it is a disk-shaped sort of pancake of stars. But how big was that pancake, and what was its structure? The first attempt at trying to figure that out was in the late 1700s by William Herschel and his sister Caroline Herschel. William Herschel is best known as the discoverer of the planet Uranus. They made a map of the Milky Way by just basically pointing their telescope in different directions and counting the number of stars. It was very tedious work. Basically, it had to be done by eye. This was before the advent of photographic film. And what they came up with was something that looked like this, although somewhat three-dimensional. It was kind of a blob of stars that was sort of elongated in the horizontal direction here. It was shorter in this direction. And on this side, this was actually quite interesting. This thing that looks kind of like a beak or alligator jaws was what we now know to be pointing toward the center of the galaxy. You may remember from the image of the Milky Way yesterday, there was a dark lane running across the middle of the picture of the Milky Way. But we now know that that lane is caused by dust clouds that are obscuring the starlight behind it. But they didn't know that. They thought there was sort of a gap in the stars here, and that's what caused this sort of funny beak or jaws going out this side. Our solar system would have been here more or less at the center, and so, not surprisingly, you see fewer stars if you look this way or this way, and you see more stars if you look this way, but especially if you look to the right, which we now know actually it does not end here, but goes on for quite a ways. In the early 1920s, an astronomer by the name of Harlow Shapley decided to test this assumption by using variable stars to find the distances to star clusters. He noticed something very interesting in the night sky, and this is something that pretty much most dedicated backyard astronomers understand. There are two types of star cluster. One is called an open cluster. They used to be called galactic clusters, but that was too confusing because it sounded like a cluster of galaxies. But an open cluster is a cluster similar to like the Pleiades. The Pleiades are the famous seven sisters in the constellation Taurus. It's a smattering of maybe a few dozen to several hundred, up to maybe 1,000 stars. And these star clusters are generally very young. They have a number of blue stars in them. Basically, these are clusters of stars that all formed from the same molecular cloud at pretty much the same time. Globular clusters, on the other hand, are much larger. On average, they're much farther away, and they tend to have a spherical shape, like a globe. That's where the name comes from. They tend to be highly concentrated with stars in the center. In fact, if you were at the center of one of these globular clusters, the night sky would be so bright you could probably read a book by starlight. Excuse me. And then the cluster kind of thins out as you go outward. Typical diameter of a globular cluster is maybe 75 light years. And the thing that Shapley noticed was that they were distributed in a very different way in the sky. These open clusters tended to always be in the general direction of the band of light we call the Milky Way. So you notice that open clusters lie near the plane of the Milky Way in the sky. So if we imagine that our galaxy is shaped like this funny shaped disk, the open clusters would have been to the left and to the right and sort of circular all around. If you imagine looking sort of at a pancake on sideways, that's the direction that the open clusters would be in. They would be circling you in sort of a band, just like the band of the Milky Way circles you. Globular clusters, on the other hand, are very unusual because, first of all, they tend to be found above and below the plane of the Milky Way. And they tend to be all on the right-hand side in this diagram. They tend to be all on one side of the sky and not on the other. Okay? And this direction is the direction toward what we call the constellation of Sagittarius. The constellation of Sagittarius is a famous constellation pattern in the sky. And it's not a place in our galaxy, it's just a direction from our Earth that we say that's the direction toward Sagittarius. And so when you look to that direction, that's where the swarm of globular clusters seems to be centered around. So they're all in this direction, and this arrow here pointing almost directly to the constellation of Sagittarius. In fact, that's where the funny beak is sort of pointed toward. Well, Shapley thought this can't be a coincidence. What I'm going to do, he said, is I'm going to find the distance of those globular clusters. And what he used were variable stars. Now, he didn't use Cepheids. Cepheids are not very common in globular clusters. But there is a type of variable star globular clusters that's very common. They're called RR Lyra stars. They all seem to have about the same brightness. They all vary about the same short period of maybe a day or so. And by using those variable stars, he was able to make a three-dimensional map of globular clusters. So here's our funny disc-shaped Herschel galaxy, which he and his sister thought this was the entire Milky Way. This was later modified into what's called the Captain universe. When you look toward this direction of the sky and measure the distance to all these globular clusters, they tend to make almost like a cluster of clusters. And the center of the cluster of clusters is right around here. And Shapley said, you know, that can't be just some random place in space. There must be some sort of center of mass, some sort of attractor, some sort of balancing point about which all these globular clusters are orbiting. Okay. So he found the distances to these globular clusters using the RR Lyra variables and made a three-dimensional map of them. And he found that the swarm of clusters were centered on a point thousands of light years away, in fact tens of thousands of light years away, in the general direction of the constellation of Sagittarius. Now the stars that make up the constellation of Sagittarius are probably somewhere around here, and they're all at different distances. But when you look from Earth toward that direction, you look toward the center of mass of these globular clusters. He postulated that this, the center of the swarm, was the center of our galaxy. So instead of the galaxy looking like this, the galaxy we now know actually looks something like this. He quadrupled the size, the measured size. Okay, he didn't actually quadruple the size of the galaxy. He quadrupled the measured size of our galaxy, and found that we're actually about 2/3 of the way out from the center toward the edge. And that's approximately 30,000 light years. You'll see figures that vary from 26 to 30,000 light years. Let's, just to keep it simple to remember, let's just round it up to 30,000 light years. So this is what our Milky Way would look like as seen from the side. We have the central bulge, we have this disk. Because of the dust, we can only see this portion of our cloud, and this is what the Herschels saw. Okay? These yellow dots are the globular clusters, which orbit like little miniature galaxies about our main galaxy, the Milky Way. So let's sort of look at the components of the Milky Way. Again, when we look at it edge on, we have the disk. The disk is anywhere between 3,000 light years and 30,000 light years thick. The central portion of the disk is very, very thin. The galactic bulge is much thicker, and that tends to be about 30,000 light years thick. And so you have two kind of components. You have what's called the spherical component, which consists of the globular clusters and the nucleus, the nuclear bulge, and a smattering of sort of runaway stars that are all just kind of swarming around the center, like that. And you have the disk, which is a rotating, well, I don't know about rotating because it's not a solid object, but it goes around the center of the galaxy very similar to the way our planets go around the sun, in the same basic plane of rotation, of orbiting. It was once thought that the spherical component formed first and then the rotating galaxy collapsed to a disk shape because the spherical component tends to be older and the disk component tends to be made of younger material. But galactic evolution is still a very poorly understood thing, and ideas about it are changing all the time. Okay, so the disk component contains all the matter confined to the plane of rotation. There are, of course, stars. This is one of my favorite star clusters in the night sky. It's called the double cluster in the constellation of Perseus. On a nice dark night, you can actually see it with the naked eye without binoculars or anything like that. It is two very rich open clusters. An association would be a smaller version of one of these clusters. They're between 10 and 100 stars that all form together, as well as open clusters. All these stars here are probably siblings of each other that formed at the same time out of the same molecular cloud. You also have emission nebula. Remember H2 regions, emission nebulas? And you also have dust and molecular clouds. The central dust lane is actually very, very thin, something like 300 light years thick, whereas the disk is more like 3,000 light years thick, and the bulge is around 30,000 light years thick. Vertically speaking. So most of the dust in the young bright stars are confined to a disk only 3,000 light years thick. You can almost think of this as kind of a sandwich, and the dust is like the filling of the sandwich, and the disk itself is sort of the bread and the filling. You also have spiral arms. Okay, spiral arms are kind of a weird pinwheel structure. Not weird, but very pretty pinwheel structure that galaxies similar to ours seem to share. Now, it looks as though it's like a real pinwheel, where these are connected things, connected structures. We now know that that's not true. They're more like waves. When you see a wave in the water, the waves moving through the water look like a continuous thing, but in fact, the water molecules as the wave moves on are totally different from the water molecules that were forming the wave just a few seconds before. Okay, so spiral arms are really sort of where material gets bunched up, very much like water in a wave. Okay, we'll continue more with the aspects of our galaxy in part 3.